Ladder logic is one of the 5 PLC programming languages in the IEC 61131-3 standard. If you're starting to tune out, stick around a bit longer. Maybe we'll convince you to keep watching. You won't hear anything more about IEC 61131-3. By the end of the video, you'll be able to read a standard industrial program and understand exactly how the machine thinks. Ladder logic was the first PLC language developed and remains the most widely used today. We don't want to bore you with historical reminiscing, but ladder logic was designed to resemble the electrical schematic diagrams of hardwired relay logic. This made it very popular among non-programmers, such as electricians and other maintenance personnel. Ladder logic isn't just about looking like an electrical schematic. It's about understanding system operation and real-time troubleshooting. In a factory, seeing rung instructions go true or false is much faster than debugging lines of code. All right, let's get to it. This electrical schematic is a classic motor start-stop configuration. The stop switch, start switch, and control relay are hardwired together to operate a motor. Historically, for ease of understanding and standardization, this type of electrical circuit was drawn to look like a ladder, and has remained so today. How does it work? Pushing the start button energized CR1. Contacts 8 and 6 close and keep CR1 energized after the start button is released. Contacts 1 and 3 close, and the motor starts. Pushing the stop switch breaks the CR1 energizing path, and the motor stops. Looking at a different schematic version of the same electrical circuit, the relay ladder version is the clear winner for interpreting circuit action. Okay, let's forget about that ugly second schematic and focus on the relay ladder version. We said earlier that the stop switch, start switch, and control relay were hardwired together to operate a motor. Making changes or replacing defective components often required cutting wires or, at the very least, removing them from terminals and rewiring the entire system. PLCs came along and made things so much easier. We got rid of all the hardwiring and many of the components. If you are an operations manager or a maintenance manager looking to train your technical team on the specific equipment you have on site, RealPAR's custom training might be the right fit for you. Our instructors can develop custom technical training on topics like PLC programming and troubleshooting, industrial networking, PID controllers, and other subjects related to industrial automation. These classes can be held online with a live instructor, or we can conduct the training on site at your facility using your own PLC panels to train your team. To learn more, you can visit realpars.com/custom-training and fill out the form. You can also find the link in the video description. Let's look at how PLCs and ladder logic perform the motor stop-start action. We still need the stop and start buttons, but say goodbye to the control relay CR1. The stop and start switches are no longer wired together. Each switch is connected to a separate input on the PLC. This is oversimplified, but you probably get the picture. The motor is connected to an output of the PLC. This is another simplification, as PLCs don't usually operate motors directly. But this will work for our explanation. Okay, so this is where the ladder logic program comes into play. The purpose of the ladder logic is to determine the motor's status based on the switch's status. In other words, the program examines the switch conditions and then decides what to do with the motor. How does that happen? Every vendor PLC ladder logic programming language uses symbols to represent instructions. Thankfully, the graphic symbols for these instructions are almost identical. Unfortunately, the names are not. Let's have a look at the 3 most commonly used instructions in any PLC ladder logic program. We've got 2 input instructions and 1 output instruction. The first input instruction resembles a normally open relay contact. That's exactly how it operates in ladder logic. Siemens calls it an NO contact, while Allen Bradley calls it an XIC, or examine if close contact. The second input instruction resembles a normally closed relay contact. That's exactly how it operates in ladder logic. Siemens calls it an NC contact, while Alan Bradley calls it an XIO, or examine if open contact. Here's a tip for you to remember. They are graphical instructions displayed on a screen, not physical components. They don't click shut or pop open like real contacts. For both of these instructions, closed is true and open is false. For Alan Bradley, a small green bar indicates true. The output instruction resembles a coil. Phoenix Contact calls it a coil, while Alan Bradley calls it an OTE, or output energize. Okay, so now we've investigated the three most common instructions. So what do we do with them? Well, we put them into a ladder logic program and connect them. Keep in mind that these instructions are graphical representations of computer code. Let's look at a typical ladder logic program. Think of the vertical lines on the left and right as power rails. Rungs are connected to each end of the power rails and populated with instructions. Input instructions are connected to the left-hand power rail, and output instructions to the right. The left rail is the source of logical power. For an output on the right to turn on, you have to create a continuous path of true instructions to get the logical power from the left rail to the right. Let's figure out how the first rung behaves. The motor start output will turn on when the start button and stop button instructions create a continuous path of true instructions. Why is the start button instruction false and the stop button instruction true? These input instructions receive their marching orders from the physical devices connected to the PLC. How does that happen? Inside the program, the start button instruction is configured to monitor the status of terminal 0 on the PLC input, and the stop button instruction is configured to monitor the status of terminal 3. An open path to the terminals results in a logic 0, and a closed path results in a logic 1. These logic values are stored in specific PLC memory locations. A logic 0 tells an associated instruction to remain in its present state. A logic 1 tells an associated instruction to change to its opposite state. So without pushing any physical buttons, terminal 0 will produce a logic 0. The start button instruction remains in its present false state. Terminal 3 will produce a logic 1. The stop button instruction changes to its opposite state, true. Phew! Let that sink in for a minute or two. Watch the last few minutes again if you are still a bit fuzzy. When the motor start output goes true, a logic 1 is placed in a specific memory location, causing the PLC to run the motor. What needs to happen to get the motor to run? Pressing the start switch sets the start button instruction to true, creating a continuous path of true instructions to the motor start output instruction. The motor start input instruction also goes true, providing a path around the start button instruction. Why? This will ensure that the motor continues to run even after the start switch is released. Pressing the stop switch sets the stop button instruction to false, breaking the continuous path of true instructions. The motor start instruction goes false, and the motor stops. All right, we've covered the operation of the three basic instructions and seen how they function in a simple ladder logic rung. Let's have a look at another ladder logic program and see if we can determine what it does. Based on what we've talked about in this video, let's analyze the ladder logic for an overhead door. The control console has 3 push buttons and 3 indicator lamps. The door shut output instruction is true, therefore the shut light should be on, and it is. The door ajar output instruction is false, therefore the ajar light should be off, and it is. Here's a tough question to contemplate. What type of switch is the stop switch? Is it normally open or normally closed? The stop instruction is an XIO, or normally closed, and it is currently true as indicated by the green bar. So, there must be a logic 0 stored in its allocated PLC memory location. That means that the actual stop switch must be a normally open type. Our PLC programming skill path gives you hands-on practice, real-world simulations, and practical examples to help you understand ladder logic and PLC programming in greater depth. You'll also find courses covering multiple PLC platforms and brands, so you can focus on building skills that match the equipment and systems used in your workplace. Wow, that was fun! We hope you enjoyed following along. And just like that, you've gone from staring at a drawing that made no sense to deconstructing an overhead door system. Whether you're looking at a Siemens NO contact, an Allen Bradley XIC, or a Phoenix contact coil, the logic is the same. Sort through the true and false instructions, and you'll find the answer. And if you're looking to train your entire team, RealPARS also offers custom live training tailored to your equipment and processes. Visit realpars.com/custom-training to learn more and get started.